The 16-meter ESO Very Large Telescope, the flagship project of European astronomy. Set to become the world's largest optical telescope when it enters into operation around the year 2000, it's being built by the European Southern Observatory, ESO, an intergovernmental scientific organization supported by 8 European countries. The Very Large Telescope, or VLT, is not just one single telescope, but an array of 4 telescopes, each of which has a main mirror of no less than 8.2 meters in diameter. When they work together, the 4 telescopes will have the same light-collecting surface as a 16-meter telescope. With several smaller auxiliary telescopes, the performance will be improved even further. In its most powerful mode of operation, the VLT will produce extremely sharp images. In fact, the VLT would even be capable of seeing individual astronauts on the surface of the Moon 400,000 kilometers away. The VLT's fantastic capabilities will make dreams come true for scientists. It opens the door to fascinating new research possibilities, and Europe's astronomers are eagerly looking forward to probing the universe with their new super telescope. But they must still wait a little. Engineers and other specialists at ESO, together with their partners in European industry, are still busy putting the final touch to this great project. The heart of the telescope is the main mirror. Each of the giant VLT mirrors consists of one enormous piece of special glass with a diameter of 8.2 meters. They are the largest mirrors ever produced. The Schott Glassworks in Mainz, Germany, is one of the few factories in the world capable of producing large glass mirrors. But even for the experts at Schott, the manufacture of 8-meter glass blanks was an enormous challenge. Early morning. Inside the Schott factory, the atmosphere is tense. The first 8-meter mirror is about to be cast. The mold is brought into position for the pouring. The platinum feeder nose at the bottom of the tank is heated. Suddenly, the molten glass appears. Its temperature is about 1400 degrees. The giant melting tank above holds 70 metric tons of glass. The critical pouring process must be very carefully controlled. Thermal sensors measure the temperature distribution during this operation. The glassworkers wear protective clothing against the blazing heat. Although they may resemble modern-day gladiators, they are in reality highly skilled experts and part of a dedicated team where each member has his special tasks and knows exactly how to cope with them. 4 hours later, the pouring is finished. The mold now holds 45 metric tons of glass, and the glass flow is cut off. The casting mold is moved to a rotating platform. It's still covered by an overhead heating system to prevent an inhomogeneous cooling of the surface. The giant mold starts spinning. It already has a curved base, and with the centrifugal forces created by the spin, the glass gradually assumes the rough meniscus shape required for the mirror blank. The temperature has now decreased to about 1200 degrees. The cover is removed, and for a moment the entire surface is seen. The intense energy radiated by the glass mass amounts to more than 20 megawatt. The factory hall is flooded by an intense heat wave which only ceases as the cooling lid is brought into position above the glass. The entire operation is witnessed by invited journalists. While the spinning continues, the molten glass cools down slowly, so that the glass mass retains its curved surface when it stiffens. This form of spin casting was developed by Schott especially for the purpose of making telescope mirrors of such dimensions. The mold is transferred to the so-called annealing furnace. It takes another 3 months before the enormous glass blank has cooled down to room temperature. Only then will it be known if the casting was successful. After the cooling and shrinking in the annealing furnace, the solid mirror blank is now ready for the next step, the rough machining of its surface. At this stage, the blank is extremely fragile. It requires special tools to handle such a massive piece of glass. To ensure that the handling equipment does not damage the blank, it's attached in a flexible and adaptable way to the mirror blank. First, the mirror must be turned, a most delicate maneuver. The operation begins. It takes 90 minutes to complete the turning. Schott project leaders, Drs. Müller and Hoeneß, are on the spot to check that all goes well. The mirror is moved to the grinding machine. It's lifted by a hoisting device with 18 vacuum cups. It's centered on the table and carefully lowered. During the machining process, excess glass is removed with the help of diamond grinding wheels. When finished, the 8.2-meter mirror blank is only 18 centimeters thick and weighs about 22 metric tons. When the mirror has finally attained the desired form, it again disappears into a furnace to undergo the ceramization cycle. This process lasts for 8 months, during which the glass is transformed into a ceramic material known as zero-dur. For telescope makers, the most important properties of this material are its zero thermal expansion coefficient and its extremely high homogeneity. When the mirror is mounted in the telescope, it will keep its exact shape, neither expanding nor contracting when the temperature changes. This is vital to ensure that the telescope always retains the best possible optical quality. Now, the central hole is drilled in the mirror. The concentricity of the central hole with respect to the mirror's outer edge is in the order of 10 microns. Precise quality control is required throughout the entire manufacturing process. Here, the blank is checked for possible internal stress. It is verified that ESO's very stringent demands specified in the contract for the mirrors are fully met. One and a half years after the exciting moment of the pouring, the first mirror blank is ready for delivery. During the previous days, the blank has been carefully checked by ESO experts. The world's largest mirror blank passes the critical acceptance test with flying colors. Slowly, the blank is lowered onto the support system of the container, which has been designed especially to ensure safe transportation of the fragile mirror. Only a few minutes to go before the official delivery, but the technicians are still fully concentrating on their difficult work. They must place the mirror on the support with the utmost precision, otherwise the safety of the blank during the transport cannot be ensured and the mirror might break.
10,
The removal of the handling tools marks the exact moment of delivery. ISO now possesses the world's first 8-meter mirror blank. A happy moment for all those who have contributed to this great technological feat, and also for ISO Director General Riccardo Giacconi. With this difficult task successfully accomplished, the VLT project can now continue according to schedule. The next stage is the polishing of the mirror. For this, it must leave its birthplace at the Shot Glass Works and embark on a voyage to Paris. The technicians prepare the enormous mirror for sea transportation, while project engineer Philip Dierix from ISO watches the operation. Riosc, the French optical company, has been contracted to polish the mirror. An accelerometer is attached to the container. It will accurately measure the forces acting on the mirror during the trip. These data are important to ISO in order to verify the correct design of the mirror container and to make sure that it will sustain the stress expected during the future sea transport across the Atlantic Ocean to Chile. The first leg of the long voyage has begun. With a speed of no more than 5 kilometers an hour, the special transporter takes the mirror the first few kilometers to the river port of Mainz. Here, the container is loaded onto the vessel Eldor. The blank will stay in the hold of the vessel. Again, the loading operation requires the utmost care. At 2 a.m., the vessel is ready for departure. Captain Reiter consults his charts and checks the latest weather forecasts. For the safety of the mirror, calm sea is a must, but even during summer, there is no guarantee. The ship will carry its precious cargo down the Rhine into the Channel, up the River Seine through Paris to the port of Évry, just south of the French capital, and close to the Riosc plant in Saint-Pierre-du-Perret. Four days later, in the middle of the night, the ship passes Paris. Navigating at night through the shallow waters and under the low and narrow bridges around the Ile de la Cité requires the utmost concentration on the part of the two pilots. The next morning, the ship approaches its destination, the port of Évry. Slowly, it berths and unloading begins. At midnight, the road transport to the Riosc factory is ready to depart. Again, as in Germany, the roads must be closed. The police are there to provide an escort and to make sure that the heavy Parisian night traffic does not disturb the delicate transport. The last 2 kilometers are on smaller roads. This is a real test for the truck driver. The road is barely wide enough, and now and then a branch or two are cut off, and a traffic sign has to be moved to make way for the large container. At 2:30 in the morning, the blank reaches its destination, the Riosc plant. This facility, which was built especially for the purpose, is equipped with the world's most advanced equipment for high-precision polishing of large mirrors. State-of-the-art interferometers probe the accuracy of the mirror surface as the polishing of the giant blanks proceeds. They're installed at the top level of the facility in a 30-meter high tower at the center of the mirror's radius of curvature. The work progresses over a period of 2 years. Then the time has come for the detailed acceptance tests by ESO's engineers. Careful measurements of the first mirror show that the final optical surface is correct to within 500 thousandths of a millimeter. This corresponds to an accuracy of only 1 millimeter deviation over a surface with a diameter of 165 kilometers, as large as the entire Paris area. Meanwhile, other European companies are busy with the huge telescope structures, buildings, and auxiliary instrumentation. Altogether, more than 5,000 people are involved in the VLT project. The mechanical telescope structures are assembled and tested at a factory in Italy. This pre-assembly enables ESO's engineers and technicians to verify the functionality and compliance with technical specifications before the components embark on their long voyage across the ocean to their ultimate destination, the distant VLT Observatory on Paranal, a 2,640-meter high mountain peak in the lonely South American Atacama Desert. Here, in one of the most desolate places on the surface of our planet, nature has created a remarkably dry climate. Detailed studies have confirmed that this site is one of the best locations for an astronomical observatory on Earth, providing up to 350 cloudless nights a year. Work on the telescopes continues in Europe. Meanwhile, Paranal has become a bustling construction site. A large number of specialists of many different trades and professions work together to transform the site from an isolated patch of desert to a high-tech scientific exploration base. 8 years have passed since the signing of the contract between Schott and ESO for the manufacture of the giant VLT mirror blanks. The completion of the mirrors not only marks a decisive milestone in the VLT project, it's also a model of highly successful collaboration between fundamental science and the leading high-tech industries in Europe.